Hello everyone, let's get started. So welcome to another lecture as part of our ME6151 Computational Heat and Fluid Flow. So in the last lecture, we looked at numerical diffusion and dispersion and explained these properties as they are tied to the upwind difference scheme as well as to the central difference scheme, right, from a numerical perspective. And then we also looked at kind of an introduction to unsteady convection, and we looked at the exact solution which can be used to compare now when we try to solve this equation using a finite volume method, right? So we can compare it with the exact solution and comment on the accuracy of the schemes that we are using, okay? So in continuation to what where we left off, so in today's lecture we're going to discretize this unsteady convection equation using a central difference scheme or an upwind difference scheme for the spatial derivatives. Okay, so for the spatial derivatives we will use either a central difference scheme or upwind difference scheme, and we will also use for the temporal derivatives we will either use either explicit schemes or implicit schemes. Okay. And in addition, we will also look at another particular method that is known as Lax-Van Troff discretization. And then we will also look at constructing and using some of the higher order schemes for convection. Okay. Because till now we have only looked at upwind difference scheme, which is first order accurate in space, and central difference scheme, which is second order accurate in space. Okay. Alright, let's move on. So starting with the unsteady convection equation. So if you set the gamma equal to 0 and source equal to 0 and retain the unsteady part and the advection part, then we get this partial differential equation, which is partial t rho phi plus del bar dot rho u bar phi equals 0, right? In order to simplify the analysis, we'll make a one-dimensional approximation and also set the density equal to 1. Okay, so with these two assumptions, we can now reduce this equation. With rho equal to 1, this term will become partial phi partial t plus we have nabla dot rho u bar phi, rho equals 1, and this being 1d, we will only retain one derivative, that is partial x u phi, okay, which is only the x component of this velocity vector equal to 0. To make things further simple, we are going to also assume that the mesh is uniform with a cell width of delta x. Okay. Alright, now how do we solve this unsteady convection equation? Remember, we have done the unsteady diffusion equation a while back, in which we had to integrate it not only on the control volume but also on the time step, right? As a result, now we have to integrate both in volume, both in space and time for this particular equation. So that would read integral delta t, that is time going from t to t plus delta t, and integral over the volume. In this particular case, volume happens to be delta x, so this is integral delta t, integral delta x, partial t, and then we have integration on dx dt, right, on the volume as well as on the time step, plus, and then on the second time also we have integral delta t, integral delta x, partial x u phi dx dt equal to 0. Okay. Now, of course, we know how to now integrate these two quantities both on space and time. So we can write the first quantity as phi p minus phi p0 times delta x, right? Because this will simplify to partial t dt, which will give you phi, and phi value at the cell centroid can be taken assuming that it prevails over the entire cell. So this will be phi p minus phi p0 times, of course, the volume would be integral times delta x, right? Plus, now how do we integrate this particular candidate? Essentially, we have we apply the Gauss divergence theorem. Then partial x u phi dx would give you u phi on the face on both the faces, right? This is u phi on the east minus u phi on the west. Plus, we also have a profile assumption for variation of this flux with time, right? That means that we'll introduce a factor f times the quantity u phi east minus u phi w plus 1 minus f times u phi east at the previous time level, u phi east 0 minus u phi west 0, right? Times, of course, this entire thing, because being a linear profile assumption, has to be multiplied with delta t to account for the integration of this quantity. Okay, so this is the discretized equation for the volume and time integrated unsteady convection equation here. Okay. Now depending on the method that we choose, either the value of f will be decided, and similarly depending on the spatial method that we choose, the approximation for the phase values of the dependent variable will be evaluated. Okay, so if we use an explicit method for the time step, then f would be taken to be 0. So if you set f equal to 0, the method would be explicit, in which case this entire thing would go to 0, right? Only the second term remains here, only this term remains, and we also say if we use a central difference scheme, then phi little east and phi little west would be taken as arithmetic average of the east value and the p value, and the west value and the p value, right? We also assume that u is constant and it is positive. In this particular case, it doesn't matter because it's a central difference scheme. So irrespective of the direction of velocity, the value on the phi on the faces is always computed as the arithmetic average. Okay. All right. Then what we have is phi p minus phi p 0 times delta x. So we also want to kind of divide divide by delta x times delta t, okay, throughout this equation. That means we will get delta x gets cancelled, we get a delta t in the denominator. So the first term would be phi p minus phi p 0 upon delta t, plus this term is 0, right? So essentially, because what we have is an explicit method, right? So f equal to 0 for that will give you this quantity is 0, right? And only this quantity remains, and phi little e equals phi e plus pp by 2. So as a result, what you get is you get a p here and a half p here and a half p here, both of which get cancelled, right? And then remaining terms would be u upon del x del t gets cancelled with this delta t, so you get u upon delta x, and there is a 2 in the denominator, so you get u upon 2 delta x times phi capital E comes from here minus phi capital W, both evaluated at the previous time level equal to 0. Okay, so this is the equation when explicit time stepping and central difference scheme is used to discretize this particular one-dimensional wave equation. Okay, now now of course this is an explicit method, so do we have to solve for a system of linear equations in order to do this? So no need to solve for a system, right? Because this is an explicit equation, so you can directly substitute for the right hand side values and then calculate what is phi p. Of course, we can do a truncation error analysis on this thing, right? On this particular discretized equation to know what is the spatial and temporal order of accuracy. And also we can do a von Neumann stability analysis, right, and see if that is stable or not. Similarly, we can also understand what is the modified equation for this to see whether it works or not. Okay, so if you look at the truncation error, of course, without doing the truncation error, we know that the explicit scheme is only first order accurate in time, and the central difference scheme is second order accurate in space. Okay, so from the truncation error analysis, we can write that this is order delta t and order delta x square. Okay, so which I have not done, but you have to do it and check. And again, the von Neumann stability analysis we've performed, it shows that essentially this is unconditionally unstable. Okay, so this method is unconditionally unstable. So what does that mean? That means that this cannot be used under any circumstances, because no matter what delta t you choose, this is always unstable. But this is an explicit method. So what does instability mean? This is an explicit method, and this is also for an unsteady equation. As a result, as you go ahead with calculating phi p by substituting phi p 0, phi e 0, phi w 0 from the previous time step values, phi p gets to unbounded values as you go with time. Okay, as you go with time. So that is the meaning for unconditionally unstable. Okay, that means this method cannot be used. So it cannot be used. As a result, of course, we cannot go ahead with this method. So we need to change something to get a better method. Alright, if you look at the modified equation, which you have to derive, okay, which I have not done, so you need to derive. What you see is that the modified equation for this particular scheme reads as partial phi partial t plus u dou phi dou x. This is basically the same as the original equation that we started off with, okay, with assuming u equal to constant. On the right hand side, what you see is you see minus u square delta t by 2 dou square phi by dou x square. Okay, so the term on the right hand side has a second derivative. So this is more like a what? This is more like a diffusion term, right? This is more like a diffusion like behavior, whereas the diffusion constant itself is actually a function of delta t, and not only that, there is a minus sign here. So the gamma that we would choose till now is now a corresponding value here, it has a negative. So this is more like anti-diffusion, right? This is kind of a negative artificial viscosity. So we know that if there is a positive viscosity, that tends to suppress the instabilities, right? Essentially it's going to introduce a diffusion like behavior because it is multiplying an even order derivative. Whereas if you have a negative value for the viscosity like coefficient, so what does that mean? What does that mean if you're having a negative diffusivity? What will it do to the equation? Essentially it will introduce, instead of damping, instead of reducing the amplitude, it's going to make it unstable, right? So no doubt why we saw a similar behavior coming from our von Neumann stability analysis, which says that it is unconditionally unstable, and the reason for this instability is basically the negative diffusion that is coming up, which can be explained through the modified equation as well, okay? So as a result, the explicit central difference scheme, when applied to the wave equation, cannot be used, okay? So it cannot be used to solve this particular wave equation, okay? Then of course we can look at changing either the spatial scheme, or we can look at changing the time stepping scheme. Let us first look at changing the time stepping scheme. Instead of having an explicit method, let us have an implicit method for the time derivative and a central difference scheme as usual for the spatial derivative. Okay, now if we do this, of course we have the original equation. Because the spatial scheme is not different, it is basically, so essentially we are substituting for what here, f equals 1, because this is implicit method, and the central difference approximation is the same, okay? That means we go back here. Now this term gets retained, whereas this term, so this term gets retained because f equals 1 and this term goes to 0. So all our values are now evaluated at time level 1, right, or at delta t. So that is the only difference. That means we get rid of these superscripts here. So as a result, our discretized equation reads as Vp minus Vp0 upon delta t. Of course, here again we are dividing everything with delta x and delta t. Plus you have u upon 2 delta x times phi capital east minus phi w. These are evaluated at the current time level. Now how do we solve for this equation? Do we need to solve for a system? Do we need to solve for a linear system of equations? Yes, we need to solve for a linear system. That means at every delta t you have to solve for a linear system, right? Because this is an implicit method, right? So as at every delta time a linear system needs to be solved, okay? Okay, all right. What about the truncation error? The truncation error remains the same. We know that the implicit method and the explicit method both have order delta t in time and order delta x square in space. So this is the same thing. What about the von Neumann stability analysis? Von Neumann stability analysis, if you perform, which I am not doing here, so you need to kind of perform this step and see. If you perform von Neumann stability analysis, then what you get is, it says that the method is unconditionally stable. Okay, that is good news, because the method is unconditionally stable. This can be used, of course, maybe for simulations. Okay, but what happens is, if you look at the modified equation, so if you look at the modified equation, what we get is basically partial phi plus u partial phi partial x equals, you get a plus instead of minus, right? In this case you get a minus, and here in this case you get a plus. Is that easy to see? Is that straightforward to see? Because we have just changed the time stepping here. Maybe if you perform a modified equation, you will be able to see that. Okay, so essentially u square delta t by 2 dou square v by dou t square. So that means again we got a diffusion like term, right? And then there is a positive value for the diffusion coefficient. So that means this also acts like mostly like an upwind scheme, right? Essentially it's going to introduce some kind of diffusion. I mean, that is what we think. But however, if you look at if you actually try to solve the system, although this is unconditionally stable, what you see is that your solution would kind of give you a stable solution, but the results will not be accurate for any delta t you choose. That is because the von Neumann stability analysis only tells you that it is unconditionally stable. That means it's not going to be unbounded, it's not going to be infinite values for any of these solution variables, but it doesn't guarantee that it will give you the correct answer. Okay, so the stability analysis only tells you whether it is gives you boundedness or not, or it gives you stable solutions or not, but it doesn't tell you whether it is accurate or not. Okay, so that this doesn't mean that it will be accurate or correct, or physically whether it is possible or not. That behavior can be explained by looking at the coefficients, right? In our regular analysis, we always look at the coefficients. So if I rewrite this equation by sending everything to the right hand side, we know that there are the coefficients here, one has a positive sign and one has a negative sign, right? Now it doesn't matter whatever delta t we take, the A east and A west will always have opposite signs, right? So that means I can rewrite this as phi p equals phi p0 plus u delta t by 2 delta x equals phi east minus phi west, right? So we can write that here. This should be a minus here. Okay, so this should be a minus because I have sent it to the right hand side. Okay, so this is not a plus, this is a minus. Fine. All right, so that means what we have here is that we have the coefficients being opposite signs. This would always produce oscillations, right? This will produce oscillations as a result of the negative coefficients that we have. Okay, and doesn't matter whatever delta t we take, this will always produce oscillations. Okay, so that's the reason why the solution will not be physically correct. However, the results will be bounded, so you will get still some numbers which will not grow to infinite or something, but this method would not be of use because we cannot really use the obtained solution to compare with anything. Okay, so essentially both the methods that we have seen till now, either the implicit or the explicit time stepping methods, together with the central difference scheme, are not of any use. Okay, all right, so we could not solve for it. Now let us explore the other two methods, which are either the implicit or explicit, but used in the context of the upwind difference schemes. Okay, all right, let us look at the upwind difference schemes. So let us get started again with explicit method for time stepping and upwind difference scheme for the spatial derivatives. Okay, so because it is explicit, we expect that everything to be valued at the previous time level. That means everything will have a superscript of 0. The unsteady term remains as it is. This is phi p minus phi p0 upon delta t. Now we make an assumption that the velocity is positive. Okay, because upwind scheme requires you to have kind of depends on the direction. So as a result, I make u is greater than 0. Okay, so basically once u is greater than 0, we can write for phi. Remember, this term is basically phi little east, and this term is our phi little w, right? Because this is basically you have u is greater than 0, so phi east will be equal to phi p, and this quantity would be equal to phi capital W, right? This is on the west face. On the west face, if u west is also positive, then this will be phi W, right? You need to verify this once again. All right, so we have this particular equation, which is discretization with explicit time stepping and upwind difference scheme. Okay, now of course if you perform truncation analysis, what you get is you get a first order in space and first order in time, because upwind difference scheme is first order in space as well. Okay. Now if you perform von Neumann stability analysis, what you see is that the method says this is conditionally stable. Okay. So conditionally stable, which means that essentially if you choose the, so that means this method can be used depending on under certain conditions of your delta t. Okay. So which is basically which tells you and the stability condition you would get from the stability analysis is basically u delta t by delta x, which is a particular ratio, should be between 0 and 1. So if it is between 0 and 1, then this method can be used to get your correct results. Okay. So that means this method can be used. Now let's look at the modified equation to kind of describe its behavior. So the modified equation looks like partial phi partial t plus u partial phi partial x equals. Now on the right hand side again we have a second order derivative, which is similar to the diffusion like behavior. Okay. Not only that, we have also the diffusion coefficient is now u delta x by 2 times 1 minus nu. Okay. This nu is nothing but the u delta t by delta x. Okay. So this is basically the same the value here we have now called it as nu. Okay. So if I say nu is u delta t by delta x, which is in the literature referred to as either Courant number or it is actually referred to as CFL number, which is named after Courant, Fredericks and Levy after the scientist who first proposed this particular who first performed the stability analysis and discovered this thing. Okay. So as a result, if we can choose delta t such that it is less than delta x by u, then we can certainly work with the equation in integrating this thing. Okay. So now let us come back to our heuristic analysis, where we can rewrite this equation as phi p equals phi p0 by delta t, right? This is phi p0 times 1 minus u delta t. So I'm sending everything to the right hand side, and then this becomes u delta t by delta x times phi w0. Okay. So this is basically what we get. Okay. So if I do this, this is basically what we get. Now this equation is nothing but if I replace u delta t by delta x with nu, what we get is phi p0 times 1 minus nu plus nu times phi w0. Okay. Now what we see is, if, because we said from the stability analysis, if nu can be taken to be between 0 and 1, then it turns out then both coefficients are always positive, isn't it? Which was not the case when we had implicit CDS, right? No matter what delta t you take, the coefficients were always coming out to be, some coefficients are coming out to be negative, because there the coefficients were in terms of phi p, phi east and phi w, whereas here we have only two in terms of phi p and phi w. As a result, the term coming from the unsteady can be clubbed with the one of the spatial values. Okay. So that means if nu can be taken to be between 0 and 1, that means this will be positive, and of course this will be positive. As a result, both the coefficients will be positive, and this equation would give you stable solutions and physically possible solution without oscillations, right? Because the coefficients will be, both the coefficients will be positive. All right. So as a result, the explicit plus upwind difference scheme can be used to solve the unsteady convection equation. Okay. So it can be used. Okay. We now found one method to solve our equation. All right. Now, do we need to solve for a system here, a system of linear equations? No, we don't have to, because this is an explicit method. Everything is known on the right hand side, and it can be just substituted, and we can get the value of phi p at every delta t. Only condition is that your delta t cannot be any random number, rather it has to be between to satisfy the CFL number criteria, right? So it has to be between 0 and 1, the u delta t by delta x. Okay, so that is the only condition that is put on the method. All right. Now let us see if we can use this explicit upwind difference scheme to solve, let's say, our wave equation with two initial conditions. One set of problem would be with an initial condition of a sine wave. The other one would be with a, so one would be with a sine wave, the other one would be with a square pulse. Okay. Now we assume that we have, let's say, periodic boundary conditions. What does that mean? That means that in the x direction we have periodic boundary conditions. So if something is leaving through the domain through one direction, it will come back through the left hand side. Okay, if it leaves the right hand side, it will come back through the left hand side. That is a periodic boundary condition. That's what we implemented in the code. So what does it mean? How do you implement a periodic boundary condition? You implement a periodic boundary condition by saying that your east neighbor for the cell that is near the boundary would be same as this guy, right, on the left hand side here. Okay, let us see. Okay, let us look at this example problem, convection of an initial profile. We know that the exact solution is basically the same profile shifted by u times time, right? Velocity times the time is what the shift is. Now we will use explicit and upwind difference scheme for time stepping and spatial derivative, and of course also use periodic boundary conditions in the x direction. So here on the left hand side you see a initial sine wave, on the right hand side you see the problem of the square pulse. So let us see if you have, so I have periodic boundary conditions here and here. That means whatever goes out of here will come back from here. Now the initial profile is shown here in black. Okay, this is basically approximately a sine wave. Okay, and this sine wave, the exact solution also after one period, that means it will travel, it will come back, and it will come back to the same location. So we have solved the problem, let's say, for one time period. Okay, one period of this travel. So it has come back to the same location. So the exact solution also coincides with the initial profile. Okay, that is with the black one. Now if we had solved it using explicit and upwind difference scheme, the result you would obtain is basically shown in red color here, where you can see that there is a decrease in amplitude. So we start off with this black profile and solve the system using explicit upwind difference scheme. Then the solution after one period of revolution or one period of movement would be equal to the one shown by red, right? So you can see that there is a diffusion that is coming into here. This diffusion is basically dictated or controlled because of the term we saw here, right? Based on u delta x by 2 times 1 minus nu. This is the diffusion coefficient. Depending on how large delta x, delta t we take, the amount of diffusion we see here will be controlled. Okay. But one thing we see is that there are no wiggles in the solution, right? That is because we have not used a CDS scheme, rather we have used an upwind difference scheme. So we see some artificial diffusion, right? We see artificial diffusion, which is a characteristic of the upwind difference scheme, right? Because of the even order derivative in the modified equation. Okay. Now what about on the right hand side? So on the right hand side we again start off with a square pulse, that is the black solution, that is our initial profile. And again we apply periodic boundary conditions. So the square pulse essentially moves, okay, the square pulse moves like this to the right hand side, and once it reaches the boundary it will start coming back from the left hand side. Okay, so we again have periodic boundary condition, and we let it come back to the same position, to the same location, that is one cycle of revolution. And we again start off, so that is the exact solution dictated by phi of x minus ut, the exact solution for the pure convection equation. Now if we solve again this initial profile that is shown in the black with explicit and upwind difference scheme, what you see is that you see again a profile that does not have any wiggles, but it has a decrease in amplitude, right? You again see a diffusion like behavior, that is because of the even order derivative that is coming up in the modified equation. Okay, so this is a solution. Of course it is not exact, rather it gives you a solution which is kind of diffusive in nature, but without any wiggles. Okay, so explicit upwind difference scheme can be used with a proper delta x delta t, such that we can get somewhat okay results with by using the method. Okay. Now one question here is that we have solved it, let's say, for one period of revolution. Now let's say if we keep doing this with explicit UDS for, let's say, few hundreds of cycles, what will happen to this peak? Would it be the same, or would it reduce? Or in the or in the let's say in the limit of t tends to infinity, what would be the amplitude that you see here predicted using the upwind difference and the explicit method? What would that be? What will happen to this amplitude? Would it remain the same as you go with time, or would it, of course it will shift, right? It will shift, it will come back, but the next time it comes back here, would that be smaller or would that be the same? That should be smaller, right? Because continuously as you are integrating the equation, your diffusion is taking away the energy from the solution, right? So as a result, it will be smaller and smaller, and what will happen in the limit of infinite amplitude? The exact solution will remain the same because it dictates that it has to preserve the amplitude and it only shifts in location, whereas if you solve it with one of these methods, eventually the amplitude will go to 0, right? Everything will disappear. Okay. All right. Alright, now that means we found one method of doing or solving this unsteady convection equation, that is the explicit upwind difference scheme. Now what about the implicit upwind difference scheme? Would that work or would it not work? Will an implicit UDS work? That is something you have to find out, and you can again perform truncation error analysis. Of course, if you do this thing, you know that this is order delta t and order delta x, right? This you already know. If you perform stability analysis, you need to see what you would get. Okay, would it be unconditionally stable or unconditionally unstable or whatever it is? So you need to perform a stability analysis, and also you need to look at a modified equation for this and comment on the solution. Okay, that is something I leave it for you to do. Okay, of course you can draw similar conclusions by looking at how this term will be, right? We have done it for the implicit CDS, so you can see how the modified equation looks like and so on by looking at the explicit method as well. All right. So we have now, out of these 4 methods, we have looked at one of the methods. Now of course the upwind difference schemes are viable. They can be used for the solution, but the issue is that the upwind difference schemes are also diffusive, right? When we looked at the central difference schemes, they cannot be directly used either with explicit or implicit methods, but one property that the central difference schemes has is they are dispersive in nature. However, they also have this artificial viscosity, the negative viscosity that is coming into play. However, they are not dissipative, so they kind of preserve the amplitude, right, which is a good thing. So several attempts have been made in the literature and several modifications have been done, and one of such schemes is basically a Lax-Mandrav scheme, which is basically tries to address tries to fix the problems associated with the explicit CDS method. Okay, so it will take basically the explicit central difference scheme, which will not work because of the negative viscosity that we have in the modified equation, and it will try to fix that such that it works. Okay, so essentially if you would recall the explicit CDS method, the modified equation for explicit CDS method, what we got was partial phi partial t plus u partial phi partial x equals minus u square delta t by 2 dou square phi by dou x square. We said this is more like a diffusion like term, and then the negative viscosity, negative diffusion coefficient is what is causing the problem in terms of instability. Okay, so the idea is, can we get rid of this coefficient or this particular term from this modified equation? Okay, so that means yes, we can. Essentially, we should not solve for partial phi partial t plus u partial phi partial x equal to 0 in the first place. Rather, if you add a positive value of the same quantity to the equation, that means instead of solving for the originally wave equation, if you would solve for, you add a plus here, right, to the original equation, such that in the modified equation, when you get this minus, this gets cancelled with this plus. Okay, so if you start off with this problem instead of the original problem, then you will not have the negative viscosity coming into play in the modified equation. As a result, it will work fine. So that is the idea with which it was started off with. So instead of solving with this, you start off with essentially a wave equation with a diffusion like term on the right hand side, where the diffusion coefficient is basically your negative of what you get in the modified equation. That means it's a positive u square delta t by 2 dou square phi by dou x square. Okay. So this is basically changing the problem. So you are asked to solve for a 1D wave equation, and instead you will not solve for it because you want to work with explicit central difference scheme. You will solve a different equation with something else on the right hand side, which would have a better behavior. Okay, so that is what Lax and Van Roff proposed, and that's what Lax-Van Roff scheme is applied to 1D wave equation. Okay, all right, then that means now how do we discretize this equation? So we actually made it now second order derivative here. So our now starting point is this equation, that is partial phi partial t plus u partial phi partial x equals u square delta t upon 2 times dou square phi by dou x square. That is our starting point. Now in the Lax-Van Roff scheme, we again use explicit method, that means and central difference scheme for these derivatives, and also we need to now come up with central difference scheme for the second derivative, that is the partial square phi by partial x square. Okay, so what we have is, for the first term we have phi p minus phi 0, phi p minus phi p 0 by delta t, plus the second term is u times this is basically when you integrate and substitute for phi little east and phi little w, you get phi capital E 0 minus phi capital W 0 upon 2 delta x. That is what you get. And on the right hand side, what you get is u square delta t by 2, and the second derivative here, it appears as if we have substituted using a finite difference formula, but this is done with finite volume. You get pretty much the same result here. So you get basically partial phi partial x east minus partial phi partial x west, and each of them would have phi east minus phi p minus phi west minus phi p minus phi west. That will give rise to minus 2 phi p and all other terms. And when you had divided with delta x delta t, there is already a delta x here, and this becomes delta x square. Okay, and there is a delta t that comes up in the numerator as well. Okay, this is basically coming because of the extra term we started off with. Okay, so this is the discretization for the Lax-Van Roff method. Okay, all right, now we can of course do a truncation error analysis and von Neumann stability analysis, and we can look at the modified equation for this Lax-Van Roff scheme. That means we are looking at a modified equation for the modified wave equation. Okay, so that means if you do a truncation error analysis, which I have not done here, which you know how to do it, so if you kind of derive this part, this is basically gives you second order accuracy in space. That is because of the central difference schemes we have used, and it also gives you second order accuracy in time. That is because of these terms that are coming up here. Okay, so this you need to verify. Now if you perform von Neumann stability analysis for this Lax-Van Roff scheme, what you get is essentially your u delta t by delta x, the CFL number, has to be between -1 to 1. So it only gives you a conditional stability. That means you have to choose your delta t such that it is kind of satisfies this condition, and if you can choose it that way, then the method would be stable. Okay, so we have changed the unconditionally stable method, right, which was originally you remember the explicit CDS was unconditionally unstable, right? So that we have changed it to now conditionally stable method by incorporating this extra second order derivative on the right hand side. Okay, that's what Lax-Van Roff scheme has done. All right, now we can look at the modified equation for the Lax-Van Roff method. That means we are looking at modified equation for this guy, right? So which of course will not have this particular term, because this gets cancelled with whatever term that usually you get, and you get now a third order derivative. So the modified equation would read partial phi partial t plus u partial phi partial x equals, you get some number times partial cube phi by partial x cube. So you get a third derivative with something multiplying it, which is basically in terms of your CFL number and order delta x square. So this is basically telling you your method is second order accurate, and this being a third derivative, this is basically what kind of a term is this? This is dispersive, right? So this is not dissipative, it produces dispersion. So depending on u delta t by delta x value, this we can solve for the method, right? Alright, so that means let us look at an example problem. Example problem is again the same sine wave and the step function. So on the left hand side here we have the sine wave, where again the black denotes the initial condition or the exact solution after one cycle of revolution, and the red denotes the solution obtained using the Lax-Van Troff scheme. Okay, so what we see is that because there is no dissipation like term, unlike the upwind difference scheme, we see that the peaks are now very much preserved. Okay, I have drawn this red to be somewhat closer to this, but it is exactly overlying on top of it. I just drew it very close such that you can perceive it. Okay, so there is no diffusion. However, you see that where there are discontinuities, you see again some kind of wiggles that show up. Okay, this is because of the dispersive nature. Okay. Again, if you look at the sine wave, what you have is the black one is the initial condition as well as the exact solution after one cycle of revolution. That means having periodic boundary conditions on the left and right. The red one, as you can see, preserves the amplitude, but again at the locations where there is a jump in the solution, you get some kind of oscillations that come up. This is again because of the dispersive nature of the method. Okay. However, the Lax-Van Troff seems to be much better than upwind difference scheme, which produced differences in the amplitudes. Okay, so as a result, there are several other methods which are proposed, which will try to fix these oscillations as well, and particularly some of them are in the class where we look at we kind of construct higher order schemes for upwind differencing, because upwind difference schemes would not produce these oscillations. As a result, the upwind difference schemes are somewhat preferred because you don't get new maxima and minima. Rather, what you get is your amplitude, decrease in amplitude can be fixed by going to higher order. Okay, so the next topic is basically construction and use of higher order schemes. Those are based on upwind difference method. Okay, so up till now we have looked at the first order upwind difference scheme and the second order central difference schemes, but these per se as such are not very usable because the upwind difference schemes are more diffusive in nature, and the central difference schemes are, although they are dispersive in nature, they cannot be used because of the problems with unconditional instability and these things. So as a result, the higher order schemes are proposed, which are based on the higher order, which are based on the upwind difference schemes. Okay, but constructed to the higher order. All right. So now we will see how to construct the higher order schemes. So the convection term we get is basically in the form of Fe times phi east. Okay, and if Fe is positive, that means the velocity on the face is positive, then phi little east equals phi capital P. That's what we have. So we construct everything for this particular condition. Okay, so I use this condition, okay, and construct all the schemes, and later on you would realize how to change this, how to modify this for the other conditions that exist. Okay. So that means if Fe is greater than or equal to 0, of course this can be written always. I can write phi of x, that is phi in the neighborhood of xp, can be written in terms of the phi p, right? The value of phi at the cell centroid p. This is basically using Taylor series expansion. So we can expand using Taylor series. This is phi of x equals phi p plus x minus xp partial phi partial x, plus you get the second derivative, that is x minus xp square upon 2 factorial times partial square phi by partial x square, and so on. Okay. Now up till now, for the first order UDS, this is our first order upwind difference scheme, right? Essentially, if you only consider this first term here, then this gave you your first order UDS, right? The upwind difference scheme. Now, if you include not only the first term, if you also include the gradient term, that means the first two terms in the Taylor series, then what you're going to get is basically a second order accurate scheme. Of course, now we need to introduce an approximation not only for the phase value but also for the gradient. Okay, just like the way we have done it for the diffusion terms. Now if you include first three terms, then the other term, this would be of the order delta x cube, so you get a third order accurate scheme, and so on. So depending on the number of terms you retain in the Taylor series expansion for phi of x, we can get more and more accurate schemes for the upwind differencing of the quantity, dependent quantity phi. Okay, so let us look at, by including the first two terms, let us construct something known as a second order accurate upwind scheme by including the first two terms. That means phi of x equals phi p plus x minus xp partial phi partial xp plus this is basically plus this is order delta x square, right? This is basically order delta x square, second order accurate in space. So again, I assume that the mass flow rate, the Fe is greater than or equal to 0. Then we need to see how to calculate, how do I approximate phi sub e. Okay, we know that now the x location is basically x little e, which is, that means xe minus xp would be equal to how much? Delta x by 2, right? The distance between the east face and the cell centroid P would be delta x by 2. Okay, that means I want to calculate what is phi at xe, which is nothing but phi e equals phi p plus xe minus xp times partial phi partial x at p. Okay, so this is nothing but phi e is phi p plus xe minus xp is delta x by 2 times partial phi partial x at p. Now how do we evaluate this particular derivative? That again defines a particular second order upwind difference scheme. Okay, so we can of course write this in two ways. One is using a central difference formula, that is phi partial x at p can be written as, in central difference terms, this is phi east minus phi west by 2 delta x, that is the distance between east and west, and which will give you phi little e equals phi p plus phi east minus phi w by 4, right? Because you have a 2 here and you have a 2 here, and delta x gets cancelled, right? We're just substituting for partial phi partial x from, basically we are substituting partial phi partial x from here into this term here, right? So if we substitute for this, then we get for phi little east equals phi p plus 1/4 phi east minus phi w by 4. So this particular scheme of evaluating the gradient, the first derivative using central difference formula, gives you something known as Fromm scheme. Okay, so this is what is referred to it in the literature as. Now similarly, the first derivative can also be approximated using a backward difference formula, right? Because you have phi p, it can be phi p minus phi w by delta x. Now why can't we use a forward difference formula here? That is because we have assumed Fe to be greater than 0, right? So either you can use a central difference or a backward difference, because flow is going from left to right. So you cannot use the forward difference here, right? Phi east minus phi p would try to, you can actually use it, but it will lead to instabilities. You can actually try that. Okay, so that's why this is phi p minus phi w by delta x using a backward difference formula, one-sided formula. This will give you phi little e equals phi p plus, there is no 2 here, there is a 2 here, so this will be phi p minus phi w by 2, right? The delta x gets cancelled. So this particular scheme is known as beam warming scheme. Now of course this becomes phi p minus phi east minus phi p if Fe is negative, if Fe is less than 0. Okay, so this basically now gave you two schemes which are both second order accurate, okay, and both are second order accurate upwind difference schemes. Okay, now of course remember that all these things are derived for Fe greater than or equal to 0, so you need to modify them accordingly for other phases and for other values of Fe, if Fe is less than 0 and so on. Another thing is these are all derived for assuming a uniform mesh, so you need to fix things if mesh is not uniform. Okay, all right, then if you include let's say the first two terms, then what you get is basically a third order upwind scheme that would read as phi of x equals phi p plus x minus xp partial phi partial x plus x minus xp square by 2 factorial partial square phi by partial x square p plus order delta x cube. Okay, so this is basically a third order accurate scheme. Of course, just like what we have done for the first derivative, now we have to also model we have to also introduce something, some kind of a model for the second derivative as well, right? We have done this for the first derivative, now we have to do something for the second derivative as well. So if we can do this, then the scheme is complete, right? So we need to evaluate partial phi partial xp and partial square phi by partial x square at p. Now again, depending on what schemes you use, you get a particular final scheme. Okay, so if you use a central difference scheme for evaluating derivatives, then you get a particular scheme. Okay, now again I am assuming that Fe is positive and we want to calculate what is phi on the phase east. Okay, so if we use central difference scheme, we can write the first derivative as phi east minus phi w by 2 delta x, and the second derivative as phi east minus 2 phi p plus phi w by delta x square. Okay, so if I plug in these two back into the original equation here and substitute for x east minus xp as delta x by 2 and x east minus xp as delta x by 2 whole square, then what you get is you get an equation for phi little e as phi p plus delta x by 2 times this quantity partial phi partial x plus delta x square by, you get a 8, right? You have a 2 coming from here and there is already a 2 in the denominator, times the second derivative plus order delta x cube. So if you simplify this, what you get is phi p plus phi east minus phi w by 4 plus phi east minus 2 phi b plus phi 8 by 8. Okay, remember this entire thing only works for Fe greater than or equal to 0. So if Fe is not greater than or equal to 0, if Fe is negative, what would you do? Essentially, if Fe is negative, where do you start off with? Fe is negative, you start off with, do you write phi e little e equals phi p? No. We start off with, if Fe is negative, we start off with phi capital E, right? So this would, you start off with phi capital E and try expanding about the east xe, right? That's where you start off, and then you have to substitute the central difference formula for these in terms of the centered around E cell. Okay, that's what you have to do, and so on. Similarly, you have to do all these things for the other phases, Fw and Fw when it is positive, the phi w when Fw is positive and negative. Okay, so we have only done for one case. Okay, so this particular scheme that we got by using the central difference schemes for the first and second derivatives in the Taylor series expansion for phi e is known as, in the literature known as quick scheme, which is third order accurate, which stands for quadratic upwind interpolation for convective kinetics. Okay, this is basically quadratic, is basically second order interpolation. That's what we have used. That's why it's called quadratic upwind interpolation. Now this is upwind is because all this will work for Fe greater than or equal to 0. We have developed in terms of phi p. Okay, that is the upwind part here, but not these parts. These are always central differences. Okay, so accordingly that means you get another formula for phi little e if Fe is negative. Similarly, you get one formula when Fw is positive for phi little w, and one formula for phi w when Fw is negative. Okay, fine. So that may not be in terms of let's say for example if your Fe is negative, then what do you expect? What would be your phi p? Phi p would be shifted to phi capital E, right? This would be phi capital E. And what would be the central differencing for Fe less than 0? If Fe is less than 0, your central cell is basically phi capital E. Then the central difference formula would read this as east would be your east, and then this would be your west will be P cell. So this will be east minus P. And similarly, this will be east, and this will be east, and this will be P, right? And so on. So accordingly, you have to develop for the west phase. You have to write for essentially when Fw is greater than 0 and Fw is less than 0, you need to come up with formulae for phi sub w, okay, or phi sub little w. All right, so that kind of finishes the two higher order schemes, or the three higher order schemes. That is basically Fromm scheme, Beam-Warman scheme, and then the quick scheme, the quadratic upwind interpolation for convective kinetics. All right, now we're going to stop here. So in the next lecture we'll pick up from these higher order schemes. How do we implement them actually in the code, and then we move on to the discussions on the unstructured meshes, right? Because till now we have not looked at unstructured meshes for convection. Okay, so that will be kind of the agenda for the next lecture. Okay, I'm going to stop here. If you have any questions, write back to me. We will discuss them. All right, thank you. Talk to you in the next class.